Hello, welcome to my talk for RailsConf 2021. My name is Gannon, and this is Profiling to Make Your Rails app faster. I'll start with a little bit about myself. I'm a Rails committer and a big fan of the Ruby open source community. I'm currently number 55 on the Rails contributors board. As of recording, I have 246 commits on Rails. I have a cat. His name is Waz. He's the reason I'm sane enough to give this talk in these socially distant times. You may hear him over the course of this presentation. I work for a company called Shopify on the Code Foundations team. One of our main focuses is to improve the developer experience on the Shopify monolith. If you haven't heard of the monolith, it's a really big Rails app, probably one of the largest in the world. The origin of this talk dates back to 2019, where I attended Ruby Kaigi in Japan. It was my first conference and tons of fun to attend. The closing keynote by Jeremy Evans talked about all the optimizations he made to the SQL and Rhoda gems. To be frank, it blew my mind. I won't spoil it for you if you haven't seen it, but it taught me so much about code optimization. After watching, I knew I wanted to learn more. Later that year, I went to RailsConf in Minneapolis and attended a talk by Nate Berkopec on the basics of benchmarking and profiling. Another amazing talk. I had previously known about profilers, but didn't really understand how they worked. This talk really put things into perspective for me. A few months later, I was finally ready to show the world what I had learned. I wrote an article on how to write fast code for the Shopify engineering blog. It made it to Hacker News and got a lot of reads. The following year, I co-authored a follow-up article on how to fix slow code with Jay Lim. Fast forwarding to February of this year, my coworker Chris Salzberg started a project where he took a look at how slow the monolith was. He found there were many areas that needed improvement. 2020 was a big year for Shopify, and a lot of rush development had taken its toll. Nobody had paid much attention to keeping things fast, and it turns out you can introduce a lot of speed regressions over the course of a year. After seeing the success Chris was having fixing performance problems, I thought to myself, what about every other Rails app in the world? I'm sure many of them could use a deep dive on speed optimization. So I submitted a talk proposal about profiling to RailsConf, and here we are. This talk follows the story of a Rails app, one that was built by a contractor for a small company. Taking a look at the app, we've got views that index and show products. We've got a cart view where we can add and remove products. And finally, we've got views to perform checkouts. Pretty simple, right? Just a quick side note, this is a talk about profiling and not writing style sheets. I'm not very good at making websites look nice, so please pretend it looks professional. One day, the company hires a new developer to start working on the app. And surprise, it's you! On your first day, your boss tells you there's a problem with the website. It's slow, and you've got to fix it. So what do? Well, after some panic Googling, you come up with some answers that look pretty reasonable. You could add some indexes to your database. That might help speed up queries. Oh, and n+1 queries are bad, aren't they? We should probably have less of those. Maybe you're putting off upgrading to the next version of Ruby. That wouldn't hurt to do. Modern web tooling uses a lot of JavaScript. Maybe we could use more of that. The problem is, authors of performance optimizing articles don't know what's actually wrong with your app. Many of them have recommendations that are generally good that you should be doing, but might not fix your actual problem. This can lead to premature optimization and unnecessary complexity in your app. What we want is a tool to help narrow down performance problems, not recommendations on Rails best practices. Eventually, you come across a suggestion that piques your interest. Profiling. That might be helpful, but how can we apply it to our app? Well, if we look at our app's gem file, we'll see Rachmany Profiler. That seems like a good lead. Reading up on the gem, we'll find that it's middleware that displays a speed badge on HTML pages. It can do database profiling, call stack profiling, and memory profiling. For those of you unfamiliar with middleware, it's essentially code that runs on the server before a request is routed to your application code. It runs between you and your app code. For reference, Rails ships with a lot of middleware by default. One of which that you're probably familiar with is the debug exceptions middleware. The debug exceptions middleware bubbles up development stack traces to your browser. It's an exciting time to be learning about Rachmany Profiler. If you're on Rails 6.1.3 or later, Rachmany Profiler is included by default. But if not, you can always add it to your gem file. If we boot our app, once the page loads, you'll find the previously mentioned speed badge on the top left hand of the page. It shows how long the page took to load and how many requests were made. Now that we know what Rachmany Profiler is, let's talk about its features, starting with database profiling. If we click on the speed badge, we'll get a breakdown of partials rendered and SQL queries executed. Clicking on SQL queries will expand on the exact queries that were executed with stack traces and timings. You might find their overall concept familiar. In essence, it's the same information that Rails server logs get you. Here's the log for the same request. You'll notice it lists SQL queries, memory allocation counts, and render timings for views. Speaking of memory allocation, let's talk about Rachmany Profiler's next feature, memory profiling. This feature requires a gem to work. You'll need to add memory profiler to your gem file. With memory profiler bundled, we can reboot our app and visit the product index. Using the query parameter pp equals profile memory, we can get a report of how Ruby allocates memory for our request. The report is fairly plain looking, but very detailed. It revolves around two concepts, allocated memory and retained memory. We can see that Ruby allocates 2.8 megabytes of objects while building our view and retains 0.2 objects, 0.2 megabytes of objects. Memory profiler can be used on its own to profile arbitrary blocks of code. This is essentially what Rachmany Profiler is doing for you at the middleware level. Some of you may be wondering what the difference is between retained and allocated memory. To put it simply, allocated memory is all the memory your computer takes to perform an operation. This could be responding to a web request, running bundle install, or executing a method. Retained memory is memory that remains allocated after the operation is completed. Let's look at an example. If we were to profile a simple object creation, we would find that it allocates one object and retains no objects. This is because the object lives within the context of the profiling block and gets cleaned up afterward. If we were to assign the object to a constant, we suddenly have retained memory, because constants are global. They're something that lives beyond the scope of a profiling block. Through this example, we can assume that retained memory is always equal to or less than allocated memory for any operation. Now that we understand memory profiling, let's talk about Rachmany Profiler's last feature, call stack profiling. Like memory profiling, call stack profiling requires another gem. This time, it's the stackprof gem. So if we add stackprof to our gem file and use the query parameter pp equals flamegraph, we should get a report detailing the call stacks Ruby ran through to respond to our request. When we do that, we're greeted by a graph with lots going on. Before we get into what it all means, we should talk about where the data is coming from. Stackprof collects call stacks. You're probably most familiar with call stacks from exceptions. When an exception is raised, Ruby prints a stack trace, which is a summary of the call stack that led to the error. These call stacks are gathered by observing running code and taking snapshots at scheduled intervals. We use this data to paint a picture of what your program is doing. An important note to make is that stackprof is a sampling profiler, which means it doesn't exhaustively snapshot all call stacks for a given operation. The sample rate can be tweaked to show more or less data. As for what stackprof measures while taking snapshots, this is where the different profiling modes come in. The three modes are wall, CPU, and object. Wall time is time as you and I know it. You can think of a wall clock. Wall time is the default profiling mode that you'll want to use 90% of the time. You've probably seen CPU time before in Activity Monitor or some other task management program. This essentially means the time your computer spends thinking about something. Object mode aims to solve the same problem as memory profiler by counting new object allocations. Typically, you'll want to reach for memory profiler when measuring allocations because it's more detailed. Like memory profiler, stackprof can be used on its own to profile arbitrary blocks of code. We'll explore this usage a little bit more later. Now let's talk about the graph we saw earlier. They're called flame graphs. They look like this. Flame graphs are a standard way for viewing profiling data. On the x-axis, we've got wall time, and on the y-axis, we've got call stack depth. Below the preview window, there's a larger, more interactive view of the graph. Rachmany Profiler generates flame graphs with Speedscope. Speedscope is a profile viewer written in TypeScript. It supports a variety of formats from different profilers across different languages. However, there are a few ways you can generate a flame graph. If you're familiar with RBSpy, profiles collected with that tool look like this. RBSpy uses the original Perl script made by the creator of flame graphs, Brendan Gregg. But it's the same concept, more or less. The call stack depth on the y-axis can also be inverted on some graphs. This is how classic flame graphs look. But the look of the flame graph is dependent on the viewer that you're using. Flame graphs can come in various shapes and sizes. A great feature of Speedscope is the different ways you can choose to view the data. You can toggle between time order, left heavy, and sandwich modes. Time order is the standard view we've already seen, time on the x-axis, and stack depth on the y. Left heavy is where things get interesting. Time is on the x-axis, but no longer in sequence. Similar call stacks are grouped, so you can easily see combined timings for the slowest methods. For example, it's a little hard to see, but garbage collection occurs multiple times in time order, but is grouped into a single entry and left heavy. Sandwich starts with a sortable list of call stack methods. You can sort by self time and total time. Self is how much time is spent inside a specific method, whereas total time is the combined time spent in the specific method in any nested method call. If we click on a method in this view, we can see its position and total time as a flame graph. In this call, we can see action controller is routing to our controller and rendering a view. While it doesn't take very long to actually call our controller, the total time for processing end-to-end takes the majority of the profile. Putting it all together, we can see Rack Mini Profiler has a lot to offer. The speed badges for rendering summaries, memory profiling for object allocation counts, and call stack profiling for call stack analysis. There are even more features you can access with the pp equals help query parameter. Now, that's all great, but we haven't solved anything in our app yet. Now that we know the basics of Rack Mini Profiler and Friends, let's use it to solve some of our issues. After getting a report from your boss that customers have been complaining about slow checkouts, you have something to work off of. Equipped with your newfound profiling superpowers, you head to work. First off, on the checkout page, we're going to want to add the flame graph query parameter. We can do this by either injecting it in the view or with the web inspector of our favorite browser. When we submit the form, we can see a flame graph. In the preview at the top, we can see a few interesting things. There are several long plateaus in the graph, showing we're spending a lot of time doing just a few things. If we switch the view to left heavy, we can see that there are just two things that are taking the majority of our time. The first is capturing a checkout payment. The second is sending a confirmation email. If we assume we're using a payment gateway and a remote mail server, we find ourselves in an interesting problem. Both of these issues stem from talking to remote servers. Often, we can't control all bottlenecks within our system. The controller that initiates these communications look like this. When the order is created, we need to confirm it. For expensive or time-consuming operations we can't optimize like these, we can use ActiveJob. That allows us to move this logic over to a job class. The order confirmation job encapsulates payment capture and mailing work, so we can treat it as a single entity. Jobs can be worked on asynchronously in development or pushed to another worker process in production. Back in our controller, we can replace the previous code with a reference to our new job, telling Rails to do it later in the background. Asynchronous jobs in development work by default, but in production, it's best practice to use a queuing system. A good choice would be to use a gem like Sidekick. We can spin up another profile and see our order confirmations are now being pushed to the background. This leaves our controller faster and our users happier. For more information on jobs, the Rails guide on ActiveJob is helpful. After successfully speeding up checkouts, your boss is impressed. He mentions it would be nice if we could load the products page faster. Curious, you decide to investigate. If we break out Rack Mini Profiler again on the products index, we'll see a lot of spikes. Each spike appears to be a product partial rendering. Well, an easy answer to this would be to paginate our records. You'll inevitably encounter a view issue you can't design your way out of. The view looks like this. We loop through all of our products and render a partial for each one. Here, we can use caching to reduce the amount of repetitive work that we're doing. Caching allows us to do the work once and store the result for subsequent use. With this syntax, we can render a collection of product partials and cache them in one line. Now, Rails doesn't normally use cache stores in development mode, so you'll need to use the dev cache command in order to enable it. When you're done, running dev cache again will toggle the feature back off. So after enable caching in development mode and profiling again, we can see that our cache hits drive down our response time from 600 milliseconds to about 40 milliseconds. That's about a 15x improvement. Even on a small Rails app with simple views, caching can make a huge difference. But caching is a rather complex topic. I recommend consulting the Rails guide to see all of your options. A few months goes by and you've built up your app quite a lot. The production site is working great and your users aren't complaining. Life is good. Until one day, you start to notice your app is taking a long time to start up, and tests that were once fast are starting to crawl. What could be going on? Well, to better understand the problem, we need to know how development mode is different from production mode. Let's take a look at the different environments of Rails. This is one level deep in our app directory. This is where our autoload paths live. Each of these subfolders is autoloaded, with the exception to folders that don't contain Ruby files. So assets, JavaScript, and views are ignored. In development, these paths are searched whenever your application code references an undefined constant. Rails will try to find and load a constant based on the files it can see in these paths. In production, on the other hand, these paths are eager loaded. This means that your autoload paths are iterated and required on boot. This slows down application startup time in favor of speeding up request time for our users. In test mode, we can assume roughly the same behavior as development mode. Rails will autoload the exact same way. This means we want to do as little as possible in development and test, mostly because we don't know why the app is going to be booted. It could be to do a checkout, to run a model test, or to open the Rails console, for example. Production is the complete opposite. We want to do as much work as possible up front to optimize for our users and for our infrastructure. Typically, our app will only be booted to handle web requests and perform jobs in production. These two ideals are constantly at odds with each other. It makes it really difficult for developers to account for both while developing features. Like I mentioned earlier, you can use StackProf on its own to profile any code. With a little extra work, we can even instrument our profiles to be opened with Speedscope. Now, this is a little bit of a hack, but this code will profile any code you place between it and open it up in Speedscope. Like StackProf's run method, start and stop can be used to profile. These methods are helpful for code that doesn't fit neatly into a block. The raw option and JSON generate help output a format that Speedscope can understand. The system call here shells out our profile file to Speedscope. So if we start to profile in our application file, we can get a pulse on what our app is doing at startup. After we've required gems and before our app class is defined is a good place to start. Then we can stop when the application is fully initialized. Using these two ifs, we can capture the entire boot process in our profile. Since we aren't leveraging Rachmani Profiler anymore, we need to use our own instance of Speedscope. Luckily, it can be downloaded via a node package. After adding Speedscope to our app, we're ready to start profiling. We can start our server with the boot profile environment variable to get a profile to open up in our browser. It should look something like this. If you look closely, there's something called Spring in our call stacks. Most Rails apps use the Spring gem to start up faster. Spring boots your server once and then keeps it running in the background for future runs. This, unfortunately, can skew our profiling results. Due to the hidden nature of Spring, it can lead to a lot of confusing scenarios. A lot of people on the internet dislike this gem and will tell you to remove it from your project. This, however, is bad advice. As your Rails app grows, Spring will save you a lot of time in standard development flows, so please don't remove it. To bypass Spring for profiling, we can use the disable Spring environment variable to get more accurate data. With Spring disabled, if we do a boot time profile again, we can see Spring is no longer in our call stacks. Now that we're profiling boot, we notice one day that our app's startup time has regressed multiple seconds. Something needs to be done. Profiling boot, we can see a severe regression related to reading network buffers. If we look a little ways up the stack, we can see our shipping rates initializer is the problem. It looks like something is hanging when downloading shipping rates. Let's take a closer look at the module to find out more. The download rates method creates a network client and makes a request for shipping rates. This request is probably timing out. Our app needs to know how much to charge for shipping, but does it need to make this request on every boot? Probably not. There are a few ways to handle this scenario, but an easy way I can think of would be to make a rake task. This will allow us to treat shipping rate downloads as an isolated workflow. We can then optionally run the task on production deployments or manually in development. We may also want to increase the read timeout for shipping rate downloads if we find the connection is constantly timing out. With shipping rate downloads taskified, we can see we've shaved off nearly 4 seconds off our boot time. This is a huge performance win. But wait, there's more. Let's take a closer look at how shipping rates are downloaded. Depending on the size of the file, we could be writing a rather large string. This is a good excuse to try out Memory Profiler. We can wrap the content of our task like this and see what the report says. If we rerun the shipping rates task, we can see about 3.1 megabytes of allocated objects and 1.5 megabytes of retained objects. That's a little bit big. Instead, we can stream the content and build the shipping rates file line by line. Here, we can open the file in append mode and stream the HTTP request gradually. This should hopefully cause less string allocations. Sure enough, we're down about half the original allocations at roughly 1.5 megabytes allocated and only a few bytes retained. The size of the file hasn't changed, but the amount of times we've built a representation of it in memory has. As a side note, the new code is also noticeably faster. While debugging the last issue, you noticed another initializer that was showing up in our profile. Why would that be? Taking another boot time profile, we can see a sizable chunk of time taken up by the tax service. We can also see the code that triggered this load is the tax service initializer. Let's take a look at it. This is what the initializer looks like. The toPrepare callback safely autoloads code after boot and when the app needs to reload after a change. We need to find a way to keep track of the values we want to set, but defer loading the class until we actually need to use it. I should mention Rails 6 revamped autoloading with a new gem called Zeitwerk. It replaced the classic autoloader, which had a few drawbacks. One of Zeitwerk's features is the ability to define load hooks for any constant it loads. We can use it to reference Zeitwerk autoloaded code, including classes for external engines. Using a Zeitwerk onload callback, we can defer initialization until the class is referenced. This saves a lot of time in code loading and also any upfront costs with initialization. After updating the initializer to use onload callbacks, we can see we've shaved off about half a second. While this isn't a huge improvement, it becomes really important to be conscious of what constants you're referencing in large code bases. Now, most of our boot time is taken up by Rails, which is good. But you notice another place where code loading is slowing boot down. This time, it's in the app's monkey patches. This is what our patches look like. Each of these constants are autoloaded, which means that Ruby will wait to load them until they're referenced. We need to wrap the first patch in a callback to wait for active storage to append to our load paths. For the first patch, we can replace the toPrepare callback with a Zeitwerk onload hook like we did before. However, this won't work for Action Controller and Active Record. The problem is, these classes don't use Zeitwerk. It turns out autoloading and reloading constants can be somewhat confusing. It's a big reason why Rails is regarded as a magic framework. If we take a look at the guide for loading constants, we can see mention of an active support onload hook. Active support onload hooks look like this. You can hook onto a load event by name, and the block will be evaluated when called. Taking a closer look at Rails, we can see these load hooks strewn throughout the framework. Typically, they're defined at the bottom of core class files. As you can see by this grep, there's a lot of hooks to choose from. An important note to make here is autoloading isn't a feature exclusive to Zeitwerk or Rails. Ruby allows you to autoload any code with the standard library's autoload method. Zeitwerk actually uses Ruby's autoload method under the hood. The difference is that Zeitwerk automates the process of autoloading by defining load paths and using file naming conventions. With active supports on load hooks in place, we can see we're able to defer active record and action controller loading. You may notice a key difference in style between these callbacks. Zeitwerk callbacks aren't evaluated in the context of a class, whereas active support callbacks are. Taking a post profile, we can verify we're down about 150 milliseconds. Not a huge win, but these sorts of code loading issues can really add up. Now that your app is speedy in both development and production, both you and your users are happy. Life is good. Until one day, you receive a complaint about big shopping carts being slow to load. No problem, you think to yourself. You're quite good at fixing speed regressions at this point. Bring it on. You try and try, but you can't reproduce the problem locally. At this point, you start to sweat. Sometimes, performance problems can be hard to track down locally. For situations like these, profiling can be used on deployed production systems. Let's take a look at how to instrument production profiling with Rack Mini Profiler. We can authorize profiling in production with the authorize request method. This has no effect in development because profiling is always authorized in development. Plugging it into our application controller, we need to pair it with some kind of authentication method. If your app has the concept of administrators, this is pretty easy. Our app doesn't, so we're going to need to permit specific static IPs instead. But you could use simple HTTP auth or some kind of identity management, whatever you have available. After building up a big cart and profiling the page, we can see an issue stemming from the cart item model. Specifically, it looks like the product association. Taking a look at our cart view, we render a cart item partial. For each item, we load a product. This essentially means the page will execute a query for every item in our cart. Some more experienced developers will know this as an n+1 query. Now that we have a rough idea of the problem, we can start looking for a solution. If we search the active record querying guide, we'll find the includes method will solve our problem. If our cart setting code in our controller looks like this, we can use the includes method on the model class to ensure the product association is loaded with the least amount of queries. Switching back to development mode, we can see a change in even small carts. This is a good indicator our fix will help with our production woes, but what if we wanted to prove our change doesn't buckle under large amounts of data? A good tool to leverage here is benchmarking. With benchmarking, we can easily measure performance changes between two code paths or methods. As it turns out, Rails also has a tool to help us out here. The Rails generate benchmark command has everything you need to start benchmarking your own code. The benchmark generator was added in Rails 6.1, but you can get the same effect by creating benchmark scripts by hand. You'll notice when running the command it adds something to your gem file. This is the BenchmarkIPS gem. Benchmarking is an expansive topic worthy of its own talk, so I'll keep this brief. The IPS in BenchmarkIPS stands for iterations per second. The gem essentially runs the code blocks you give it as many times as possible and counts how many times the blocks were able to run. If we open the generated script, it looks like this. We can see we're using the BenchmarkIPS gem to test two code blocks named before and after. If we define a test cart with products and a method for querying, we should be able to accurately compare loading methods. Because this is just a test, we don't actually want to persist these records. For these situations, transactions are our friend. We can wrap our operations in a block and tell active record to roll back afterwards. This will revert any changes we make to our development database. Sure enough, if we run the script, we'll see something like this. Loading with includes is about 10 times faster. If we increase the cart item count, the savings only get better. Eager loading queries is definitely worth the extra code. So with that, we've reached the end of our story. We've got a lightning fast Rails app, and we've learned a few important lessons. You can use Rack Mini Profiler, Memory Profiler, StackProf, and Speedscope to find performance problems anywhere in your Rails app. You should use ActiveJob to defer work from the request response cycle. You should use caching to do expensive work once, so you can reuse it later. Code that makes sense in production may not make sense in development or test. You should bypass Spring for more accurate boot time profiles. You should memory profile complex operations to try to minimize unallocations. Be aware of the code that you're loading and use callbacks when necessary. You should use production profiling to arrive at solutions faster. And you can use benchmarking to assert speed differences between blocks of code. Many of the issues in this presentation were based off of real code. The app we worked on is available on GitHub for your reference, including some bonus content. Check the description for the link and links to other web pages I referenced in this talk. I'll end off with some thanks. Thank you to Ruby Central for allowing me to present this talk. Thank you to Shopify and my colleagues for supporting me through the making of this talk. Thank you to all the maintainers of the great gems we talked about today, and thank you for watching. I hope you learned something, and I hope I've inspired you to try profiling with your Rails apps.